All right, this is Alex coming right at you, and we're going to do this. So, we're going to talk about probability theory and the moment generating function. So, yeah, it's been a long time coming, this video, and the reason why I haven't been posting on my math channel in probably like a year, I just started a course on differential calculus on manifolds, and then I found out that it's just too tough for me to handle doing. I'm doing my PhD now. Also got music that I need to roll out. Spend time with the fam as well. So it was just too much. So instead now, what I'm going to do is I'm going to revisit. I'm going to just do random stuff that I thought was interesting, or like that I come across during my studies. Like now, for instance, I'm doing some statistical physics and like really trying to derive different types of models based on different types of phase field models based on different statistical ensembles. And in the process of doing this, I got into probability theory a little bit. And I want to share some of the things that I deem interesting, or like, that. So this one is going to be about the moment generating function. So I will assume that you have some sort of basic knowledge of mathematical probability. So the setting that we're going to use here is omega sigma p is a probability space. I don't know why this is here twice. This function right here, x, that goes from omega into r, is a random variable. And then the moment generating function is defined as the expected value of the exponential times t. So that's the moment generating function at point t. So we'll call this guy the moment generating function. That's what it's called in literature. And we're going to work with this guy and find out why this object is interesting. Well, object. It's actually, let's call it call it by its real name. So m is actually a function from r into r, because you see what happens is you plug in the t, and then if you compute the expected value of of xt exponentiated, you get a real number, of course. So it assigns all the real numbers, because you can put t, you can use anything from r, st. It assigns real numbers to those. So what we're going to do now is we're just going to prove some interesting statements, and as we go along, you are going to see why the moment generating function is interesting. So first of all, oftentimes when you come across literature that talks of the moment generating function, you will see this type of thing, usually right away without any explanation. So this is what we saw already, and then they'll put an equal sign here, and they'll write this as an infinite sum, n from zero to infinity, and like this. And they'll say, so this is because because this guy is what they call the nth moment. So then this is why you call it the moment generating function, and blah, blah, blah. But how does this come about? And is it always true? Now that's what I want to answer here, because in most texts this is glossed over. So we're gonna make another line here, and we're gonna put a statement down. So this is gonna be statement 1. And it's gonna say, okay, so x from omega into r is a random variable. And let's say that there exists a t0 greater than 0 such that for all t from the closed interval minus t0, t0, the moment generating function defined above is finite. Then for all t from this interval right here, from the open interval minus t0, t0, you can write down mxt is so the first thing, finish writing down the statement. The first thing you should note is that there are some conditions to this. So this guy right here, not automatic. What I mean by that is that you can't take this for granted, okay? The random variable, and most importantly, or most significantly, the moment generating function of the random variable needs to adhere to a condition before you can actually say that this is true. So what we're gonna do is we're gonna try to prove this. So let's go. Let's just take the moment generating function definition. So let's take a t from minus t0, t0, okay? And so, yeah, now we're gonna use measure theory. So whoever's not comfortable with general measure theory needs to either study up on it or rewrite all this using, say, absolutely continuous random variables or something like that. So what we're gonna do is we're gonna expand the definition here, expand the definition of this guy, which gives us okay, so this is just basically the definition, okay? Now, since it exists, okay, and is finite, we can expand the e to the tx in the following way. So I'm going to write the limit out here just to be very clear. K is 0 to n. And then up here you get a t to the kth power, you get an x omega to the kth power. And down here you get a k factorial. And this guy, let's just put it in for good measure. Let's just put it in brackets. And then the differential is out here. So all we've done is we've just expanded the e to the tx, which we can do because the whole thing exists and is finite. So now, basically, what we're asking is, can we swap the limit? Can we take the limit outside? Swap the limit with the integral. Okay. Kx omega. Can we do this operation? Which you can't always do. So then, of course, once you've done this operation, you can, of course, move the sum. That's a finite sum, so you can swap it with the integral free of charge and get, I'm going to change the indices here and get the desired expansion. Okay, here. Yeah, E. Of course, T can come out. Yeah, X to the power. Okay, so you get this guy. And the integral is in here, yeah? The integral is this guy right here. Okay? So, the only thing that we need to verify is this guy right here. I'll use purple. So, what kind of tool do we have? Well, one of the tools that we could use is the Lebesgue dominated convergence theorem. Okay. So the theorem states that the limit Fn d mu, this is for a general measure. You can write it down where here, this is the pointwise limit. If there exists a G non-negative integrable function, where integrable means measurable, and the integral of this guy with respect to the measure is finite, such that this guy, Fn, is dominated by G almost everywhere in, let's say, X, the measure space. Or let's find a different letter to not make it confusing. E, and that's the measure space on which Maya lives. Okay? So, what we're going to do is we're going to try to apply this theorem. So, application. In our case, Fn is, what's Fn? Our measure space is omega, so Fn omega is this sum right here, isn't it? K equals 0 to n. And what's in the sum? Tk x omega to the kth power k factorial. So that's Fn. So what we're going to essentially want to do, or what we're going to want to do, is take Fn like this. So we just got this type of expression. I'm going to suppress the omegas now, just to make it easier to write. So first we use the triangle inequality. We can definitely do that because it's a finite sum. And it's a k factorial. Now, we use the fact that these t's that we're taking are in I'm going to write it like this. So over here, t is in the open interval t0, minus t0, t0, which of course means that t absolute value is smaller than t0. So we can replace this guy with t0 to the kth power, x to the kth power, and k factorial. Now next, what we can do, oh yeah, we would like to, so we want to use the fact that t0 x, that's the moment generating function, is finite in t0. And this right here, what we have in hand is just a concatenated expansion, or like it's just the first couple of terms of e to the t0 x absolute value. So we just have to realize that this guy, I'm going to just write this down and then I'm going to delete it because I don't have enough space and write down the result of the entire calculation. So what we have here is either if x is greater or equal 0, this thing will just be k0n t0 k x k k factorial. And then if, and if x smaller than 0, k 0 n t0 k x k k factorial, and then there's a minus 1 to the kth power in here. You know what? Maybe we should do it like this. Maybe we shouldn't discuss it over here, but we should move on. Yeah, that'll be a better idea. So this guy is just part. Let me just come back over here. So this is just the first couple of terms of the expansion of e to t0 x absolute value. Now, if x is positive, then this guy is equal to what we have. Now, if x is negative, then this guy is equal to what we have. So if I add those two together, they're for sure going to be greater than this. Yeah, but if you take, if you take the last thing we've got here and the first thing, oh yeah, I gotta add a page. If you add the first thing and the last thing, what do you get? You get that this sum right here, k equals 0 n t x omega, this whole thing to the kth power, k factorial, which is what we wanted to estimate, is smaller or equal e minus t0 x omega plus e t0 x omega. So we can just use the monotonicity of the Lebesgue integral to get, sorry. So this is our, no, I gotta write that this is g, this is our g, so this is the function that dominates, the non-negative function that dominates. And also, if we take the integral of the function that dominates, this thing is finite because it's just the moment generating function minus t0 plus the moment generating function at t0, which we said was finite by assumption. So that's finite by assumption. So we found this function. We found this function g that dominates. Well, that's it, really. What this implies is we may do the swap. We may do the swap. So the swap, let's just write the swap labeled with a star, which is labeled right there. So we can just go over here and we can delete this question mark right here, because we've proven that we can do this. So now, the important takeaways are, you cannot do this thing right here just like that. You always need some sort of convergence property. In fact, the important thing here is convergence around in a neighborhood of 0, or rather, you need the moment generating function. The moment generating function mxt to be finite on some neighborhood of 0. So that was the key thing. Now there's one more thing that is relatively easy to prove, but it's good to know. Actually, so statement 2, and I think this is where I'm going to end, because I want to make shorter videos. I don't want to make it too long. But statement 2 is about the equivalence of well, you'll see. Let me just hop straight into it. So let x from omega into r be a random variable. Then let there exist Tn negative and Tp positive such that mx Tn is finite and let me do this. And mx Tp is finite. Then you get mx is finite on the open interval Tn Tp. So in essence, this basically says that finding a positive and a negative number at which the moment generating function is finite is equivalent to having it finite on an open neighborhood of 0. Because obviously, like, just, real quick, this is obvious, but, So let's say you find Tn, Tp, where it's finite, and then it'll be finite everywhere in here. And if you take epsilon, or if you're trying to find T0 such that T0 minus T0, such that on this interval the moment generating function is finite, then you just take T0 as the minimum of minus Tn and Tp. Yeah? And then you'll get that. So this statement tells you that you can find a nice little symmetric neighborhood of 0 on which it's finite if you can just find 2 points, Tn and Tp. If you find these 2 points, that implies this. And the other way around is obvious. If you have a symmetric neighborhood like this on which it's finite, then of course, for instance, t0 divided by 2 and t0 divided by 2, like these two guys are points at which the moment generating function is finite. So there we go. Now that's that. And we shall move on to proving this statement. It's quite easy. We'll just go proof. And right here, what will we do? Oh yeah, so we'll take a t from Tn, Tp, okay? The t can be written as a convex combination of Tn plus 1 minus alpha Tp. And then we'll just use the convexity of exp. We'll use it like this. So we'll just write E T X. So this is for all omega in omega. We can write this. And we can go ahead and just T is now, we'll just distribute the x omega like this, plus 1 minus alpha Tp x omega. And then convexity of the exponential function gives us the following thing. It's sometimes called the Jensen's inequality. Yeah, maybe like, just to be super clean here, I like, hate to be slow with this, but I really like going through this very like diligently. So I'm gonna do, I'll do it like this, Tnx. Again, I'll suppress the notation, 1 minus alpha Tpx omega. And at this point, we know, what do we know here? Maybe I'll suppress the omega, both of these. Yeah, so now you take the integral with respect to dp omega, and you get E Tx smaller or equal, this is the mononicity of the integral, alpha E Tnx plus 1 minus alpha Tpx. But this is finite. So this guy right here must be finite as well, which proves the statement. Alrighty, I think we'll end here. This will be today's little lesson, or whatever you want to call it. So just to recap, the main things here were that this expansion right here that you see often when it comes to the, whenever you see the moment generating function, most likely using it like this, it doesn't always come out like this. You have to have some sort of conditions so that you can perform the limit and integral swap right here. And these conditions are noted over here. You have to have the existence of a closed neighborhood containing 0, where the moment generating function is finite. And then you can infer that, or you cannot infer, but then you can say that there exists an open neighborhood on which you can write it down like this. And then the second statement was, okay, you don't really need an open neighborhood, because the existence of an open neighborhood is immediately guaranteed if you can just find 2 points, Tn and Tp, one negative, one positive, at which the moment generating function is finite. And then you will get a whole interval on which it is finite. So this is like a little bit of an introduction to the most basic things, moment generating function related. If you have any questions, feel free to plop them down in the comments. I'm going to try to make one random video a week. I think I'm going to continue doing the moment generating function, and I want to get to all the interesting stuff you can do with it. Like, the peak of this whole thing should be like to show that the trails are exponentially, the trails of a moment generating function, the trails of a probability of a random variable of which the moment generating function is finite on some open neighborhood of 0 exponentially decay. Don't worry. If I probably didn't say it clear enough, but I will clarify with a precise statement and proof later on.